For those who follow the channel, I got a bit into the repairing things, and I bought recently from the internet those power supplies. They were advertised as faulty, and in the previous episode I repaired the little one, which was more busted than it showed, and now it's time to move to the big one. I bought a bunch of MOSFETs, because there are more, plural, and some fussies, and let's see what this baby needs. Power supply to 13 volts, 200 milliamperes, and let's see how this power supply behaves on the first try. Whoa! Look at that! Look at that! That's wonderful! So even though this thing is more busted than the other one and more exploded and charred, it powers up and draws 55 milliamperes. That's awesome! Output. Do we have output? What the hell is that? 5 volts. Yes, we set the output to 5 volts to 100 milliamperes, as you can see here. Yep. Off. It goes down very, very slowly. Yeah, I can see that. Yeah. Yes. So up, it overshoots, then stabilizes, and off, it goes down very, very slowly. That's not bad for the beginning. I'm very pleased until now. Let's turn it off and head it to the desk. Yes, I've seen this powers up and outputs correctly. I want to measure if it outputs really to the this binding post. Yeah, and let's see what is the matter with this charred portion over here. If I look at the data sheet that I pulled up over the internet, it's pretty comprehensive, and even I can see the board. It's not particularly visible behind this capacitor here, but I can see this trace over there is not connected to the other one over there, and this is a MOSFET. This is the MOSFET which short circuits the output when you cut the output off, and it doesn't short the output right now. This is why the voltage drops so slowly when you turn it off. Do you want to know who's making this terrible noise? Suddenly you hear bang bang. Yeah, this is the cause. This one caused it. Yeah, you see it has a small doggy door there, and it pokes its head out and then comes back. Did you do that? Show me how you poke your head out. Yeah. And the other one making noises is this central heating. When it starts to heat, it makes that humming noise. Yes, I'm working here in the technical room. Yeah, so for the beginning, let's clear this damaged part over there, make it more visible. Yes, for that I'm going to use some isopropyl alcohol. Let's find some suitable brush, a fiberglass brush. Yes, I think it is clean enough. So, in my opinion, this trace goes all the way over there. Yeah, it's not connected to the other one because this one leads to ground. Yes, and this one leads to through this fuse to plus. Okay, so here in this place should be there is a MOSFET which shorts the output to the ground, and I'd be even able to put it back, but I don't know where the command, the gate, is coming from. Let's power this baby up again. All right. Yes, we have voltage. Yes, indeed, we have voltage. Woohoo! Voltage. Here's a little lower. 4.94. Well, so I thought this trace leads there. Let's turn off the device. Let's clean a little bit the pad over here. We still have a red LED over there. Okay, let's take off the... yeah, okay. Okay, let's measure ohmometrically, because by the looks of it, you see this is the negative rail, the negative pin of this capacitor, and the negative pin goes directly to this pad over here, like also this one and this one. And if I measure from here to the negative, bam, short, a straight short. So I should not connect this tab here, which is plus, you see, this is plus, so direct short. So the other one, yeah, I should leave it like that. I should leave it like that, between this and this, few megohms. This is this small little trace which was going under the MOSFET. Why was it going under the MOSFET? And now it's going nowhere, but where was it going? Was it going to plus over here? Moreover, there's another trace. This trace over here. I guess this one was coming to the gate. You see? If we follow the trace, I think this one was going to the gate. Because if we follow it, right here at the bottom, it goes to this transistor here. So this transistor gives the command to shut down the output there. So I'm going to measure this output of the transistor here and see if it changes when the output is on or off. Okay, it goes here at the bottom, underneath this diode, underneath this transistor, and goes right over there to this pin here. Okay, let's test this theory. So my multimeter is on beep. I put one lead there where I scratched a little bit the varnish, and one lead to this pin here. Bam, continuity. Let's power this thing up. Correct boot. Let's see if we have some voltage between the negative and this pin over here. And if I am to turn it on, nothing. In regards to plus, I have 5 volts negative. Yeah, the same. So I took a picture of this thing over there. Yes, then I searched online for this writing here, and looks like it is a MOSFET also, and the gate is towards me, source and drain. So I should check out the gate if I have a command, and on the source I have the output actually, which goes to the trace over there. So it's powered, it's output off, nothing on the gate. In regards to plus, I have exactly the output voltage, and if I turn off the output, in regards to minus, nothing. In regards to plus, it's exactly the output dropping. So this MOSFET here doesn't seem to receive a precise command on or off to put this to be MOSFET to be shorted. I don't understand. So I think I'll just leave it like that. We'll have a power supply which actually don't cut off the output that fast, but still it's a good power supply. It's controlled in current, short circuit, and the voltage output and all the rest. Yeah, I think I'll leave it like that. I'll just try to bodge these traces to look nicer and clean it a little bit, and that's it. You see the problem with these devices over here? There is no problem. People just don't understand how to use them. They abuse them and run them onto the ground. They solder, they short-circuited the fuses there, and run them at maximum power all the time, and then when they break they are just displeased and blame the manufacturer. It's doing a bad job and the devices is not good. But if you have a car, it is capable of output 5000 RPMs, and you run it with 5000 RPMs all your life, of course the engine will blow up in 1 month and you will say, oh, this car is garbage, throw it away, it's not good, the manufacturer is a con. But it's not like that. You cannot run your device at full power all the time. Yeah, for example, if you buy a very expensive one, you say the Chinese products are very cheap but very bad. They are not just very bad. Yes, they are bad, but you have to use them for what the purpose is. Yes, if you want a device to use it at full capability all the time, you buy a European or an American product, will be 10 times as expensive as this one, isn't it? Well, this is the story. You cannot run a product at full throttle all the time. Yes, it can output the specified parameters, but not for the entire life. It should be sporadically for a short period of time. Otherwise, these things just run as they should perfectly. Oh, baby, take off your clothes real slow. You can leave your head on. You can leave your head on. Oh shit, it creeped underneath the screen there. Oh, damn it. Yeah, the moisture over there is not very visible. Yeah, from this angle maybe a little bit. It will dry out eventually. I'm just curious if it can hold the output current over there. Let me see. Yes. For example, I have this 5 ohms, 6 ohms resistor. Okay. Let's set the output to 10 volts. The output current to 1 ampere. So we have 10 volts, 1 ampere, but also I have to set this power supply to more than 1 ampere. Oh yeah, isn't it? 1.5 amperes, 13 volts. Yep, yep. Power on. Let's connect the load. And bam! 5 volts, 1 ampere. Yes! 5 volts, 1 ampere. Yes! Yes! Because we have a constant current. Excellent! Ah! It burns! Yeah! That's awesome! 5 watts, 5.2 watts, and this one is 6.8 watts. Yeah, that's normal. And the output drops immediately because we have a load here. Yeah, yes, this is it. You see, if we wouldn't have a load, then the output wouldn't drop that fast. Look. Almost 10 volts output, and if we turn it off, the output drops very slowly. But on the other hand, with this one, if we disconnect the load, the output drops fairly fast. One more thing I want to rant about. Look, these pieces look almost the same. I believe it's the same manufacturer. The power boards look the same, but look at that. This one, the polarity, you see, it's plus and minus. The other one, exactly the same position. Yes, it is minus and plus. So the polarity is in reverse. What the hell? Now, look at that. This is the interface for an extension module like this Wi-Fi module over here. You see? Yeah. Look at this pinout. And look at the pinout of the other model. Look at the connectors. They are almost the same signals, but in a total different position. What the hell is that? Why would someone do that for the same manufacturer from a similar board, yet you cannot interchange this module with these two boards? Because the pins are different. This board had this Wi-Fi module inside, yeah, but this one also has a USB output. So I wanted to use this with the USB output because it already has one, yeah, and the other one doesn't have a a computer control dedicated, and I wanted to use the Wi-Fi to control it. But you cannot directly plug it in like that because the pins are scrambled. Of course, I will connect some jumper wires to connect them correctly, but still, look, the same signals but in totally different positions. Damn. The fact that the output cuts so slowly can be in fact problematic, because if you have a project and it starts smoking, you see it is powered with 12 volts and it starts smoking and you briefly cut the power. Yeah, you are very quick to react, but look how slowly the power is dropping. That's not good. On the other hand, if you had been to 12 volts and now you want to output only 3 volts. 3 volts. Yeah? Look how long it takes to drop to 3 volts. You can't wait that long. So, my proposal is to put directly in parallel on the output a 56 kilo ohm resistor, which is big enough not to show any current draw over there, but to be quick enough to discharge the output capacitors. So let's take a look at how it behaves. 56 kilo ohm resistor. No, let's do another test first. Without this load, we set the output to 12 volts and let's see how long it takes to turn off. Damn. Let's not wait any longer because it will take forever. Right, now let's connect this 55 kilo ohm resistor. You can see that it doesn't even show a current draw at 12 volts. So it doesn't really influence your reading of the screen or your interpretation of your project, you know. Look how fast it drops. In 10 seconds it went to 0, isn't it? So let's say we want from 12 volts to output only 5 volts. In a fair amount of time we went to 5 volts. Not very fast, but fast enough. And you can see that this resistor over there doesn't even show any current draw on the display. So I think I'll solder this one on the back. Pop the old fuse up and put the new fuse in. Repair complete. Good. Let's power it up again for the final test. Very, very nice. I'm so happy with this.
Houston, the Eagle has landed. Roger, Tranquility. We copy you on the ground.